Okay, going back to our Pscine tutorial, we are finally on my favorite C, which is C05. So let's already go to our 42 tutorial folder. Let's create the C05 folder. Let's get straight into it and let's see. Well, on this video, I will cover from the exercise 00 all the way to exercise 010. Exercise 8 is not necessary. So let's go exercise 00, exercise 01, exercise 02, exercise 03, 04, 05, 06, and 07. So Vim, I'm sorry, to the exercise 00, let's go. FT iterative factorial. Let's just close this window right here. Let me just get my cheat code to make it faster for everyone. So vim ft iterative factorial.c. We will include unistd and we will include stdio.h. And here we have create an iterated function that returns a number. This number is the result of a factorial operation based on the number given as a parameter. If the argument is not valid, the function should return 0. Overflow must not be handled. The function return will be undefined. Here is how it should be prototyped. So we have int ft iterative factorial int number. So we'll just create a variable called j, and j is equals to 1. So if our number is lesser than 0, we will return 0. Now, if you went to school and you know what a factorial is, well, basically it is the multiplication of the number minus 1 and beyond. For example, this is how you say the factorial. The factorial of 5 is 5 times 4 times 3 times 2 times 1. Of course, we cannot make times 0, because if we multiply any number by 0, it will be 0. And this is why j is equals to 1. So, while our number is greater than 0, we'll say that number is equals to number, we'll say that j is equals to number minus j and j minus mine. Well, for example, let's set it straight. Oh, I'm sorry, this is times j. Or if you want to make it better, star and b, and we will return j. So as you can see, on this case, our j is equals to okay, I saw this code for a while and then I thought, hold up. So let's say our number is 5, so and our j is equals to 1, okay? So we have 1 is equals to 1 times 5. So this j in the end will be 5. And we'll say number minus minus. So j, which is our 5, will be times since number was decreased by 1, it's 5 times 4, and then this loop will repeat by itself, and we return j, which is storing the value of the multiplication between a number times j and the decreasing of number. So let's say we want the factorial of 5, so we simply come here, percentage of d, /n, ft, iterative factorial number, and then we return 0. Compile it. It is 120 indeed. And if we make it by the factorial of -5, we get 0. And the factor of 0 also, as you can already guess, it's 0. And now you can do crazy things within the int type. Of course, if you want to see the factor of 120, our value will be 0 because it went to overflow, and since overflow wasn't handled, the function return will be undefined. Of course, if we work with reasonable values like the factor of 9, which is a very big number, as 1, 2, 3, it's 362,880. So now we go to where the fun is. Ft recursive factorial. Create a recursive function that returns the factorial of the number given as a parameter. If the argument is not valid, the function should return 0. Overflow must not be handled. Here's how it should be prototyped. So before I explain to you what is a recursive function, I believe showing is better than telling. Int ft recursive factorial int number. So a recursive function is a function that we basically call it on itself. And let's see the example. We won't need a j function in this case, a j variable in this case. Well, we're just simply gonna say that if nb is lesser than 0, we will return 0. And now all we are going to do is if number is equals to 1 or nb is equals to 0, we will return 1. And now we will return nb times ft of recursive factorial nb minus 1. Now, ladies and gentlemen, this is kind of confusing, but basically we're calling the function again, and when nb, since we are subtracting by 1, when it reaches 1, it will return 1. That will multiply nb by 1, and then it will multiply it by 0, which will multiply it by 1 again, which makes no difference. And when it reaches -1, it will return 0, which means it won't multiply anymore. So here we have our main function. Our number is 5 again, and then we print the percentage and ft recursive factorial nb return 0, we compile it, and 120 again. Now iterative power. So this is interesting. Vim ft iterative power dot c. Int ft iterative power int nb int power. So created an iterated function that returns the value of a power applied to a number. Any power lower than 0, return 0. Overflow must not be handled. We decided that 0 power will return 1. So let's work with this at first. Well, let's say that if power is lesser than 0, it will return 0. And then if power is equals to 1, is equals to 0, we will return 1. Now, while power is bigger than 1, we'll say that number is equals to number times power is equals to number times number. Well, we can just say that number times equal number and power minus minus, and we will return our number. So let's work with numbers we are already familiar with. So let's 5 to the int number is 5 and int power is 2. So the power of 5, the power of 2 on the number 5. I don't know how to correctly say it in English. So let's print it. Percentage d create new line ft iterative power and b and power. Let's return 0. Let's compile it, and it is indeed 25. And the power of 9 will return as 81. Amazing. And now let's go to exercise 03, which you can already get. Recursive power will basically do the same thing, following the logic of recursive factorial, but with the prime logic. ft recursive power.c. Let's include union std, and again, this is not necessary, by just like doing it. So int ft recursive power int nb int power. Again, if power is lesser than 0, we'll return 0. If power is equals, then 0, we will return 1. And now we will return that nb times ft iterative factorial nb times I'm sorry, yeah, nb and power minus 1, because we're doing the minus minus. I just had to look on my sheet because I forgot it. So int nb is equals to 5, int power is equals to 2. Let's print it. Percentage of d create new line ft recursive power number and power. Why did it show here? Let's compile our code. And I forgot a parenthesis right there. And this should be well, recursive power. When you are stupid, you really go through some funny things while programming. And there we have it, 0.5. You can check it again with any number you like 9 and 3, which is 81 times 3, which is 243, if I'm not mistaken. So Oh, yeah, because it's 81 times 9, you dumbass. Well, there I have it. Now, Fibonacci. Oh, I already get the Google for this. So, if you don't remember, the Fibonacci sequence is the responsible for creating this spiral symbol right here, and it is a sequence. Let me get this. Okay, this is the cool sequence. Well, you basically will sum the numbers with the number beforehand. So we have 0 and 1. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, 21 plus 13 is 34, 24 plus 21 is 55, etc. So create a function ft Fibonacci that returns the nth element of the Fibonacci sequence. The first element begin at the 0 index. Well, we'll consider that the Fibonacci sequence starts like this: 0, 1, 1, 2. Overflow must not be handled. Here's how it should be prototype. Obviously, the Fibonacci has to be recursive. If the index is less than 0, the function should return 1. So, Vim on the exercise 0, well, on the exercise 0, exercise 04, like reference ft Fibonacci.c. Let's include UniSCD and include SCPIO. So int ft Fibonacci index. So we already know that if the index is less than 0, we return minus 1. Minus 1. If index is equals, as you can already see, let me just check. Yeah. If it is equals to 0, we will return 0. And if the index is equal to 1, or if the index is equals to 2, we return 1. Why? Well, because you can see the first, like, technically this is the 0th. The first and the second element are 1, so we return 1. And what we will return? Well, we'll basically return our ft Fibonacci index minus 1 plus our ft Fibonacci index minus 2. And well, why are we doing this? Well, getting the example again, you can see that this is, let's say this is our index. It's our index minus 1 plus our index minus 2. So it's 3. So 3, it's the previous element plus the previous of the previous element. Like 8 is the previous, which is 5, plus the previous of the previous, which is 3. 5 plus 3 equals 8. Now, we can even, like, if you want to use Google just to check it, like let's see the 30th number of the Fibonacci sequence is 223. Now, let's say that our index, we want to find the 30th. So we print our ft Fibonacci index and here we have 233. This is the best one. The square root one is kind of confusing and kind of boring, and this is the only exercise I actually don't like, and the only exercise I don't know by heart. So I have to look at the code I already did for this one. So create a function that returns the square root of a number if it exists, so we won't be needing all those weird float numbers, or 0 if the square root is an irrational number. So let's jump straight to it. Vim ft. Every time I write it, I think of Squirt, and I'm sorry for this and any underage people watching it. I am a stupid young guy on his 20s and think of Squirt when he sees this. Well, uni std.h and include at yao.stdio.h int ft squirt int nb. So we already know that if nb is lesser than 0, we will return 0. And if our number and then we have our square roots. So int I, and I is equals to 1. If it's smaller than 0, it will return 0. So while I times I, and we'll understand it, is smaller than NB, and then if I times I is equals to NB, we will return I plus, and if not, we'll return 0. So let's say on our, let's get our main function so I explain it better for you. So we have our int number, which is 81. If you know it by heart, the square root of 81 is 9. And let's see how this works. So while I times I is smaller than NB, so we have 1 times 1 is smaller than 81. Well, it is. So this if right here will be ignored because it's not equal. Well, then we'll just iterate I. And then we have 2 plus 2 times 2 is still smaller than 81. And it will keep repeating until it reaches... sorry, this is where I messed up. It should be smaller or equal the number. Until it reaches a point where the I is 9, so 9 times 9 is smaller or equal than 81. Holy shit, it is! It is small or equal, it is equal. So if I times I, which is 81, it's equal to 81, then we have it, we'll return I. Since in this case it's 81, but we can say that it is 9 times 9. But we'll just return I, which in this case is 9. I can explain something really quickly in a decent manner and something so poorly. Anyway, percentage of D, create new line, ft squirt, and B. Return 0 gcc ft square root, and that is indeed 9. Now we can come here and play around like, oh yeah, it's square root of 121, we know it's 11, there's 11, and we have it. Oh yeah, and of course, as you might expect, if the I, we know it's not an irrational number because let's say we have 80, the square root of 80 is an irrational number, but since 8 times 8 is smaller than 80, but then 9 times 9 is bigger than 80, it will already skip all of this and just return 0. And if you want to prove it, well, you can just make it 120 because there is no actual square root for it, it returns 0. What the hell did I do? Oh, shit. Well, we can just actually do this. vimfd, okay. I already compiled it for you, right? Right. Now ft is prime. This is fun. This is low-key pretty fun. So, how do we know a number is a prime? Well, we know it if it is not divisible by 2 and 3. So, how do we present this logic? Oh yeah, and also it returns 1 if the number given as a parameter is a prime, and 0 if it isn't. 0 and 1 are not prime numbers, something they want us to remember. So vim ft is prime.c. Let's include our UniSTD and our STD and our STDIO. Int ft is prime int nb. So if nb is smaller, if nb is smaller or equal than 0, or if nb is completely equal to 0, we will return 0 because they are not. And if nb is equals to 2, or nb is equals to 3, we will return 1. And why are we doing this? Well, because we are going to do some calculations. So if number, the remainder of the division of number by 2, is completely equal to 0, we will return 0. Why? Because if it is divisible by 2, it is not a prime number. And then we say that while I times I is smaller or equal than number, and again this I times I happening again. Well, if number times 3 is equals to 0, we return 0, or else we return, I'm sorry, we return 0, but we cannot forget to do I plus equals 2, and then we return 1. So, as you can already imagine, what the hell is this I doing here? Since I forgot to declare it, in I, and I is equal to 3. I is equal to 3, I'm sorry. So, on a good example, let's go to our int main. So int number is equals to 7. We know 7 is a prime number. Percentage of d, and ft is prime number. And it gives us 1. So, how does this code is working? Well, we have I, which is 3. Okay? And let's follow the same logic. So, 3 times 3 is smaller or equals than 7. Well, it's not. I'm sorry, well, it is. So it comes to this loop. Well, since the remainder of this number, since 3, the remainder of 3 is not if number, which is 7, the remainder of it by 3 is not 0, which it isn't, we will return 0. And why are we adding it with a plus 2? Well, because we are having it with this will just be odd numbers. Since we're already calculating the remainder of 2, we don't need to calculate the remainder of 4, because of course if it is not by 2, it won't be by 4. And then we are just using even numbers: 3, 5, 7, 9, 11, 13, 15, 16, 19, etc., etc. Oh, and if you want to know, it might be a curiosity, but the int max 21, 47, 48, 36, 47 is not, or it is a prime number. It didn't compile my code, and I don't know why. Why? 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 Let me see what I did wrong. Oh, of course, I am a dumbass. This should be I. And maybe I'm using a big ass number. But yeah, number times I, and then I plus plus. Well, let's just leave the number beforehand just to check if I didn't mess up. Oh, okay. Well, it's just because the int was too big. So here comes the next of the best C ever. Vim ft find next prime.c. Include unifd.h and include fdio.age. Create a function that returns the next prime number greater or equal to the number given as an argument. So int ft find next prime int number. Well, the first thing we need to check, this is easy, is to check if the current number is a prime number, and we already did this with the function ft is prime. So we'll just basically copy and paste the function. So here we have it, our I, that is equals to 3. And we'll just ignore all the ifs and etc. because we need to just check if the next number is prime or we just need to find the next prime number. We don't need to say what is and what it isn't. So we'll jump straight to the I loop. So while I times I is smaller or equals to number. Let me just get my pretty stuff here. Or equal to number. And if number, the remainder of the division by I is equals to 0, we return 0 and we iterate I plus 2 and we return 1. Now we can already do, well, if number is smaller or equal than 1, we will return 2 because 2 is a prime number, as you can already guess. And while the opposite of ft is prime, so while ft is not prime of number plus plus, and then so basically while ft's prime doesn't return 1 but returns 0, we will iterate number, and then when it is not, we'll simply return number. So let's get our main function right here. So let's say we have 15, which is not a prime number. The next prime number is 17. ft find next prime of nb. And please return 0. Oh yeah. Int nb equals 15. Something is missing. Something is missing. Int I equals 3 while I times I is lesser or greater than b, it should return 1. What am I missing here? Again, 2 errors. My ft is prime. Oh yeah. Of course, I'm stupid. Whoa, if number times the, it should of course return 0. Okay, now I have it. And now, which is interesting is that if we put a prime number here, because again, is the next prime number greater or equal, so since 17 is already equal, when we compile it, we will get 17. But if we put 24, well, 124, I think the next is 127. If I'm not mistaken, 127. There it is. And this was the best C ever created, the math, the nerds C. Sorry for the mistaken and sorry for the FT word here, but this is how I deal with some stuff on life, and see you on C06.